the discussion today will focus on hypothesis testing using STATA. So far in this training, we have gone through, we have taken ourselves around the STATA environment, and we have also learned how we can use STATA as a calculator to do mathematical basic arithmetic calculations, as well as statistical computations. Beyond that, we have been able to learn how to understand our data by visualizing the data through graphs, plots, and also constructing summary tables, frequency distribution table, and all of that. So those things we have done, particularly, they are meant to help us to understand our data. They are not likely to be the main objective of the analysis that we want to do. So they could be to simply give us insights into the type and nature of data that we are handling. And they could also provide a pointer as to the more advanced technique that may be suitable for the analysis that we want to do. So they play a very critical role. In data science, we call what we have been doing so far as a pre-processing stage of data analytics. So they are preliminaries in a way. So at this point, most researchers, the objective of their study would be to discover a new evidence or new fact, or to either make a claim and then use statistics to establish that claim based on the evidence in the data. So the process of making a claim and then testing whether this claim is true, or to a large extent whether this reflects the situation in the population of interest. That is essentially what hypothesis testing is all about. So generally, in statistical analysis or inference, generally, all the tests are categorized into parametric and non-parametric tests. So in this, the first thing we would do would be to understand what parametric test is and what non-parametric test is. Of course, for today, the test that would be of interest to us is in the class of parametric. Maybe, though it's not listed in the outline for this training, maybe at a later date, we might also discuss non-parametric tests. Again, we will look at basic common assumptions that underlie parametric tests, and they need to be, you need to be sure that those assumptions are valid before parametric tests can be employed. So we will, after looking at those assumptions, we will check maybe one assumption which is fundamental, and then we now look at the t-test, which is very popular and common. But even then, it has a competitor, which is the normal test, z-test. So, but we are not, because of time, we will not be able to consider the two. But if you know one, you can also know the second. The only thing is, when do you use one, when do you use the other? So in STATA, I will let you know where the two of them can be assessed, and possibly you will be able to run analysis using them if the need arises. So in the t-test, there are basically, STATA provides 4 categories of t-test. The one sample, the 2 sample using groups, we'll explain those things later. And then the 2 sample using variables, and then the tiered. If you use other software like SPSS you may see two sample independent tests, you may see two sample paired tests, and some like that. So, but it's just saying the same thing in a different way. So, as I said, hypothesis testing is about making a claim. So, what an hypothesis testing is after making the claim is either the claim is true or the claim is false. So, the null hypothesis is actually the hypothesis that you specify when you know the existing situation, or maybe in literature, it's simply the hypothesis that you specify as the claim, and the alternative is the one that is against the claim. So in the null hypothesis, the focus is on the null hypothesis. So it's either you reject it or you accept it. And that is why if you reject it, then it means you're accepting the alternative. If you accept it, it means you are rejecting the alternative. So generally, to test hypothesis, you need statistical tests. So the test actually is the one that processes the data, and it's on the basis of the test that a decision is taken. So this test is again categorized into parametric and non-parametric. So this is the structure of hypothesis testing. So at this level of statistical test, there is need to now decide, should I use parametric test or should I use non-parametric test? So, but what makes the difference between parametric and non-parametric? One, it's just one thing, basically, and that is the fact that the parametric test assumes there is an underlying distribution, and the underlying distribution assumed is a normal distribution. So any distribution that has an underlying distribution, assuming that the underlying distribution is normal, then that test is parametric. So the common distribution, the common test in that category are the t-test and the Z test. Of course, you will have heard about chi-square test, but I won't talk about it because they also have the underlying assumption of a normal distribution. So there's a relationship between normal distribution and, of course, the Z distribution when it comes to the chi-square distribution, but we are not going there today. The non-parametric is distribution free. Distribution free in the sense that there is no assumption regarding the distribution, underlying the behavior of the population. So, so we call it distribution free, test. Why do we need to struggle to choose between parametric and non-parametric? It's been established, it's been statistically established that parametric tests are more powerful than the non-parametric test. So it's always the starting point. The non-parametric is, to a large extent, an alternative. And it's an alternative when you don't have idea about the underlying distribution. So it is not the first port of call when you need to do test. The parametric test is the starting point because it's more powerful terms of detecting the correct hypothesis compared to the non-parametric test. So, so in the parametric test, or whether parametric or non-parametric, you could deal with one sample and two samples. Of course, the question is, does it mean you cannot have 3, 4, 5, 6 samples? You can have. But for the discussion at hand, our focus will be on 1 or 2 samples. So when you have more than 2 samples, then you might have to use ANOVA. So that the discussion on ANOVA will come in the next week. So for now, we are dealing with 1 or 2 samples. So if it's 1 sample, then you can use the t-test or the set test. So when do you use the t-test? I will explain that in the next slide. So for the 2 samples situation, it could be that you have 2 groups, groups that are independent of one another, or you have groups that have relationship. So, so in essence, 2 cases are possible. Case where the groups are independent of one another, and the second is the case where the 2 groups are dependent. In other words, they have relationship. So as it is in parametric, so also it is in non-parametric. So, but whether 1 sample, 2 samples, that are different tests. So in the case of parametric, t-test is applicable to 1 sample. It's also applicable to 2 samples. Same for non-parametric. So the tests that are applicable are the ones shown there, but they are not our focus in this training. So what then makes the difference between the normal Z test and the student T test? That is essentially what we need to know here. So if you have the population that you are trying to study, so you need to ask yourself, let's say you have one population which you have drawn sample, independent sample from that population. So usually it's either you know the population standard deviation or you don't know the population standard deviation. You know when you draw the sample, of course, you can compute the sample mean and the sample standard deviation. So if the population standard deviation is known, in which case your answer to the question is yes, then you need to ask another question, and that is whether the sample size is greater than 30. So if it's greater than 30, it means, well, statistically, it's a large sample. So you can use the set test. So in other words, to use the set test, the population standard deviation must be known. The sample size must be large. So large here means the sample size is greater than 30. You use the t-test if the population standard deviation is known, but the sample size is small. So you now need to estimate the population standard deviation from the sample data that you have. And of course, the last possibility is that the standard deviation is not even known. And the sample size is large or small, so you use the t-test. So most often, if any of these sample size is very, let me say, the standard deviation is of the population must be, you must know it before you can use the z-test, and the sample size also must be large, that was greater than 30. So in most sensitive studies, where you cannot take large samples, you have no option but to use the t-test. And the fact is that even as your sample size gets bigger, both the t-test and the z-test will give you the same result. So the t-test, will approximate the normal test as the sample size becomes bigger. For those who know statistics, that is the result of the central limit theorem. So I think with that background, let me just stop to see if there are quick questions that I need to respond to.
Okay.
So I'm happy if there are no questions, it means the explanation is quite helpful. But if you have,
I have a question, sir.
Please go on.
Okay, sir. Thank you, sir, for the presentation. Sir, if we have more than, if the observation is more than 30 and the standard deviation is unknown, can we still go ahead to use the z-test?
If the standard deviation
is not known.
Yes.
And the population is more than 30.
Okay.
Can we still go ahead to use the z-test?
You are the one who will answer now. Look at this. Are you able to see my screen?
Yes, yes, I have the screen, yes.
Okay, so if the population standard deviation is not known.
Not known, yes.
Yes. So, and the sample size is what?
It's more than 30.
It's more than 30. Which part of this diagram falls to that condition?
Well, is the sample size above 30 under the years? Is the sample size above 30?
So it's here. If the population standard deviation is not known,
yes,
and the sample size is large,
above 30, yes, sir.
Yes, so you use the t-test.
Okay.
So that, I think I mentioned that here. The reason is that the normal distribution has two parameters that characterize the distribution. That is the mean, and then the standard deviation.
Yes,
so, and no matter the underlying distribution, whether t, chi-square, any distribution for that matter, if you take large enough sample, that distribution theoretically has been proved that it will tend towards a normal distribution.
Okay, sir.
That is the result of central limit theorem. But it's not what you should worry yourself as an applied researcher.
Okay, thank you, sir.
Excellent.
Yes, sir.
So let's now move. Here we have the starter window, and if you have your own, you will simply move to the statistics menu, and you will scroll down the first line there, the first arrow. You could also scroll to where you have the second windows, and where you have the classical test of hypothesis. So in that window, you will see t-test, mean comparison test, t-test calculator, and then next to that, so those two, you use them when your sample size is below 30 and the population standard deviation is unknown. Next to the t-test, you also have similar thing for Z test. So you have Z test, mean comparison test. This is when the population standard deviation or variance is known. So that is that, and that is the reason we are okay. Please.
No Z test. No, my whole lot. I don't know if anybody.
No Z test in your own.
Yes.
We have to report to the STATA.
Only have t-test, make compare test.
Eh?
So, I only have t-test effects based on mean comparison. T-test calculator. There's no Z test here.
What STATA version are you using?
Version 13 doesn't have it too.
Version 13.
Yes, Prof.
Okay. So you need to step up. Will you step up? Will you upgrade? In any case, it's really not. It's not something to worry about. In some situation, of course, I've told you now, even in my preliminary, in my preamble, that even if you don't have Z test and your sample size is large, the result of the T test and the Z test will be the same. Is that clear?
That's
why? Hello.
Yes.
Sorry, why is the two both the Z test and the T test will be the same?
Because of the large sample property of the normal if you have large sample, there's what we call asymptotic property. So if you have large sample, the t-test will approximate to normal, but it's only if the sample is so small. And that's why when you are doing research, we always advise that you take sufficient sample. If you take sufficient sample, it will not really matter whatever the underlying assumption distribution you assume. So the issue of normal or the issue of whether it is T or whatever will not even be an issue, because all the distributions will now tend to normal distribution.
Okay, so Prof, if I may get you clearly, in this case now that we are using Z test now for this.
No, we are using T test. Yes, we are using T test. Yes.
Then in this case that we are using Z test. I think we are using.
We are using T. We are using T for this exercise. We are using T for this exercise.
Okay.
But the point I'm making is, even if you use the T that we are going to use now, if you use it for a large sample, it will still not. It will approximate to normal, and the result will not make any difference.
Okay, sir.
Does it make sense now?
Yes, sir. But for clarification, what difference between the T test and the Z test?
I've made it clear that the T test, you use it when the population standard deviation is not known and the sample size is small.
Okay.
You use the Z test when the population standard deviation is not known and the sample size is large.
Okay.
Is that clear?
Clear, sir.
So there are other differences about the shape, but that's not my concern. I don't want to start telling you about the shape of the T, about the shape of but it's about when do we use one, when do we use the other. And it doesn't matter which one you use if the sample size is large. So I'm telling you now that if you have sample size greater than 30, close your eyes and use either Z or T, you will get the same result. Is it clear, everybody?
Yes, Prof.
Yes, Prof.
Sir.
Yes, Prof, please.
Prof, please, let's continue. Let's continue.
Okay, so let's now move to the, so where do we get the T? You go to statistics menu, and then you go to the classical test of hypothesis, and then you see the T test. So you can, of course, click on that. But before we start looking at this, I will take you back to the slide. Few more things to know about so you could also, in that statistics, you go to summary, you go to classical test. You can also look at the next, after classical test of hypothesis, you will see the battery of tests for non-parametric tests. So they are there, one sample Kolmogorov, two sample Kolmogorov, Costa-Wallis, and so on. Those are for non-parametric. I said that is not our area of concern, but this, so the classical tests, they are the parametric, the T, and so on, and the non-parametric, they are the ones you have there. So, so what makes the difference between parametric and non-parametric? Those is the underlying distribution, which I earlier mentioned to you. So all parametric tests, they have these underlying assumptions, t-test and the normal test. So one is that before you can use t-test or the normal test, the variable of interest must be on a continuous scale. So you know about the 4 levels of measurement: the nominal, the ordinal, the interval, and the ratio. So you cannot use t-test when you are dealing with categorical variables like gender, class of degree, and things like that. They are not on continuous scale. Variables like age, any variable that is measured is on continuous scale. So they are usually either the ratio scale or the interval scale. That is very important that you should know. So any like a state of origin, any categorical data, you cannot use t-test or z-test on them. So the first check you need to carry out is to ask yourself, is this variable measured? Is it measured on a continuous scale? So if the answer is yes, then you can use T or Z test. The second question is whether the sample is randomly selected. So you need to establish that the sample selection process or the process that generates the data is random. It's not only random, it's representative. So you cannot take age of females in this class only and then test hypothesis about performance and say, yes, and generalize it for this class. So you must be, you must ensure not only randomness, but representativeness. So there are, of course, ways to check whether your data is random or not, but we won't be able to do that. The third one, which is very fundamental, and which is even the more reason why we are using the test, because the test is a parametric test. The underlying assumption is that the data is normally distributed. So you must ensure that this distribution has the shape of a bell, and it's that's the shape of a normal distribution. So it's a distribution in which the mean, the median, the mode, they coincide at the middle, and they divide the distribution equally. So it's bilateral symmetrical. So it's a symmetrical distribution. So any departure from there, it could be that is skewed. So data that are skewed, you cannot use t-test. Okay. You might, to use t-test, you might need to transform the data to make it normal. So you need to check for normality, which is a critical condition for using t-test or z-test. I've mentioned this, that you must look out for the sample that you want to, the sample size. And that's one of the reasons why it's important, before you even go to the field to collect your sample, you must know the test you want to use. There is what we call sample size determination. Again, I think later in this course, or no, I'm not too sure, we'll discuss about sample size determination. So you should take reasonable sample size to be able to detect effect in your data. So if the sample size is large, then it doesn't even, that puts you in a good position, very good position. But if the sample size is very small, that puts you in a very difficult position. So always endeavor to have large enough sample to make your findings more robust. And finally is the issue of equality of variances. This is a situation where you are dealing with two independent groups. So the assumption is that the standard deviation of the two groups are the same. That is, they have the same degree of spread or dispersion. So if that happens, then t-test is valid. But if it does not happen, then you will see we have to find a way to correct that. So there are tests also to establish whether variances or standard deviation are equal or not. So we will start with checking for normative assumption of normative assumption in our data. And good enough, STATA provides 3 different tests that you can employ to check whether your data is normally distributed or not. The first one is the skewness and kurtosis test. This test requires that you have a minimum of 8 observations, for the test to run its calculations. So we will use it, and then the Shapiro-Wilk normality test, and the Shapiro-Francia normality test. So these 3 tests, they are available for use in STATA. So let's go to our STATA environment now. So so before we do that, so we can always go to table test. You can see under the distributional plots and test. If you move down, you will see below the non-parametric, you will see the skewness and kurtosis normality test, the Shapiro-Wilk normality test, the Shapiro-Francia normality test. So here you can conduct. I know that last week the lecturer spoke about plots and graphs that you can plot to visualize whether your data has a normal shape or not. That has been discussed. So beyond the visual, the test actually confirm or refute the claim of the visual. So while you cannot be 100%, you can't rest entirely on what you observed virtually. The test is very specific, and so you tend to rely more on test than virtual. So even if you still do the virtual, it's advisable that you support the virtual with the statistical test. So we will now employ the first one, stillness. But before we do that, we are going to still use our data, the auto data that we have been using. So I'm going to use the system use data, which the auto data that is inbuilt STATA. So we have the data, and I'm sure you are still familiar with the data. So it's about the make vehicle models, the price, the mileage, the repair record, and all of that. So we have the data now, and we can now look at how do we test for normality, for instance, in the mileage. So of course, we can't test for normality in the make. Let's say, so that you can see some of the part of this data. Let's say I'm interested in just this. So this is the first 5 observations for the first 3 set of variables: make, price, MPG. So make is not it's not measured on a continuous scale. It's a string variable.
Sorry, sir.
Yes.
Sorry, Prof.
Yes.
Could you repeat the command you used?
The command is there: list, make, price, MPG. We have gone beyond this. That's why I'm not going to. It's something that I expect that you will know. So I don't need to explain them in more detail again. But are you able to follow now?
Yes, we can.
We're following, sir.
So the point I'm making here is the fact that to check for normality, you cannot go and check for normality of the variable make. Variable make is a string variable. Please mute yourself. Please mute yourself. Variable make is a string variable. So it's not measured on a continuous scale. And therefore, is not subject to normality test or t-test or z-test. So, but variables like price, MPG, these variables, you can carry out normality test on them. There are other ones, yeah, but I deliberately bring out these two for purpose of explanation. So our objective is to use the skewness and kurtosis normality test. So if I click, this window will come, and you now need to select the variable you want to test. As it is, you can even see that in the skewness and kurtosis test for normality dialog box, it has on its own removed that variable make. It has removed it completely. So even if you want to choose it by error, you will not even see it.
Please, Prof, can you repeat that stage?
So you mean this, how I brought this dialog box?
Yes.
So you just go to, okay. So you go to, I'm going to close it now. This is the last time I will do it. Go to statistics, then summary, tables and tests, then go to distributional plots and tests, and then come down to skewness and kurtosis normality test. Click it to have the window. And then you see the drop-down arrow. Look for the variable of interest. But I was saying that, you know, in the data set, the variable make is not measured on a continuous scale. And you can see, even if you want to select it in this dialog box, maybe by, if you want to, either by omission or commission, it's not even going to be, it will not come up because it's string. So,
hello, Prof. Sir.
Yes, sir.
Yeah, mine has that variable make listed in this dialog box. What could be responsible, sir?
Yeah, what
it's above price.
What version?
Version 12, sir.
Okay, so those are little changes.
Differences between the versions.
Yeah, little changes
Okay,
to
sir.
help researchers,
reduce
to reduce the possibility of committing errors.
Yeah.
So they are deliberate and to help the users.
Yeah. Okay,
yes.
I understand, sir. Thank you, sir.
So you have to step up now.
Yes, sir. Okay, sir. I will, sir.
Okay. So the variable we want to use is the MPG. Of course, we could select all variables that are measured on continuous scale here, but that is not necessary. We just want to demonstrate. So as you have chosen this, you could even come to this copy command to click it, and then once you click it, come to command window and paste. So that is the command. So even without running it from the window, you get this is the result. So the result shows that you have 74 observations. This shows the probability that the test is skewed or is normal. So of course you expect the measure of skewness, not the probability. The measure of skewness is said to be equal to 0. But this is giving you probability. So don't confuse it with the measure of the skewness. So, but this is the test. This is the chi-square, the test, the adjusted chi-square test, for this skewness. And this test actually combines the skewness, that is the tail behavior, with the kurtosis, that is the peakness behavior. So in taking a decision, you have to take decision based on the joint behavior of the tail, which is the skewness, of the peakness or peakedness, which is the kurtosis. So looking at this, then we can conclude, because this is the p-value, and this p-value is far less than 0.05, which is, let's say, at alpha level of 0.05. So because of that, because this p-value is less than the alpha level of 0.05, so it means we are now going to accept our null hypothesis. So in a way, what the null we are going to reject our null hypothesis. Sorry for that. Which means that this distribution is not normal. The null hypothesis is the hypothesis that says the MPG is normally distributed. The alternative is the one that says it is not normally distributed. So if the p-value that you obtain here is smaller than the level of significance, in this case 0.05, then you reject your null hypothesis and conclude that the MPG is not normally distributed. So we could also, like I said, we could even look at two continuous variables at the same time. Let me look at MPG and trunk. So again, we can see that in the case of MPG, we reject the null hypothesis, but in the case of trunk, we cannot reject the null hypothesis. And so we can conclude that for the case of trunk, it is normally distributed, whereas for the case of MPG, it is not normally distributed. So you must always know what your null hypothesis is. So when you know your null hypothesis, that is the hypothesis you are either accepting or rejecting. So when you reject it, that's when you now accept the alternative. When you accept it, that's when you now reject the null hypothesis, the alternative. So your real focus is
sir.
the null hypothesis. Yes.
Okay, thank you, sir. I'm sorry for bringing you back, sir. From the MPG and the trunk, how are we going to reject? Is it because it's 4.19 that we are rejecting, or because the
No,
first
we
one
are
is
rejecting based on probability value. Can you see?
Probability of the sky value.
okay?
So who is talking on that case? So
Prof,
if you are,
I have a question, Prof.
let me finish with this one. I will attend to you.
Okay.
So
I'm listening, sir.
we are basing our decision. Can you see where the cursor is?
Yes, I can see it very well, sir.
So can you see probability?
Yeah, probability less greater than chi-square.
So that probability is based on this test statistic, chi-square. But don't worry yourself about that. The most important in this result is this value, which we call the p-value, So if this p-value, if it is smaller, if this p-value is smaller than your alpha level, your level of significance, that is when you reject the null hypothesis. When, I repeat, when the p-value, this probability value that is reported here, when it is smaller than your choosing level of alpha, or your alpha is also level of significance. When the p-value is smaller than the level of significance, then you reject the null hypothesis. So if our alpha is 0.05, you will see that the p-value of 0.0042 is far, far smaller than 0.05. So we are rejecting, for the case of MPG, we are rejecting the null hypothesis that it is normally distributed. And therefore, we can conclude that that MPG is not normally distributed. But the opposite is the case, which is deliberate. For the case of trunk, you will see that the case of trunk, the p-value is bigger than the alpha level that we have chosen, 0.05. And when that happens, we cannot reject the null hypothesis. And therefore, we conclude that trunk is normally distributed. Is that clear?
Hello, Prof.
Yes.
No. With my little knowledge, I learned that null hypotheses are stated in a negative form.
Don't let us go there. The hypothesis we are testing now is the null hypothesis that the variable is normally distributed. And it is the standard hypothesis. I know where you are going, but don't let us go there. If you go from here to heaven, the null hypothesis for normality test is H0. The variable is normally distributed versus H1 alternative. The variable is not normally distributed. Is that okay?
Okay.
That's my same question. That is the same question I wanted to ask, Prof.
What is the question?
Okay, what PIQ and PR critical
I can't hear you, please. So.
What do PRQ and PR critical represent in the table? Are there
I can't hear you. Please mute yourself. So yes.
I our team, what do PR skewness and PR kurtosis represent in this table? Are there the p-value?
Why do we have what?
No, what do PR skewness and PR kurtosis represent? Are there the p-value you should look at and conclude? Or
okay, can somebody who understand what he's saying help me?
Hello, is asking about the PR in skewness and the kurtosis.
The skewness and
Okay,
the
sir.
kurtosis, yes?
Yes, the PR
Sir,
and
can you hear me? What do
What is the
PR
question about them?
skewness and PR kurtosis represent in this
Okay.
table?
Yes.
Are they the p-values we should look at and conclude about the normality of those variables?
Excellent. So mute yourself. I got your question now. So the value that you see here, they are p-value testing that this variable, that the variable is not skewed. So it's looking at whether the variable is skewed or not skewed. So this p-value is what you compare also with alpha level to decide whether it is skewed or not skewed. But the second one is the one that is looking at the thickness of the variable. So if the p-value is very, it is the p-value also that you compare with the alpha to say whether the peak of this distribution is a bit higher than that of the normal distribution or lower than that of the normal distribution. But you cannot take a final decision if you don't combine the skewness and the kurtosis together. So the joint that we are using is the one that combines both the skewness and the kurtosis, and that is the one we will use to take a final decision. The variable may not be skewed, but the kurtosis may be excess. So we talk about excess kurtosis, or may have maybe lower than the thickness of a normal distribution. So you have to combine both the skewness, the information from the skewness and the information from the kurtosis to be able to take a final decision. Is that clear? So we now move
Yes,
to
it is
another.
okay.
Great, thank you. We now move to another round of tests, normality test, and that is the Shapiro-Wilk normality test. To do that, you can simply, please mute yourself. Please mute yourself. Some people, yes, please mute yourself. So let's go again to another test. This time around, you will see the Shapiro-Wilk test. So let's use the same MPG, and then you can just copy that and paste. Let's see whether
video.
Yes. Huh?
Sorry, Prof, for taking you back.
I say,
But if I follow your slides, I see that there's a test there which you wrote in the command. Not just, but we haven't practiced here.
Sorry, I can't hear you.
There's a test that is in your slides.
Yes.
It is called test MPG, no adjust.
Okay, you can do that. I'm looking at the time. This is we have a long way to go, and if I waste too much time on one, and you know the way you are asking questions,
okay.
So all those other ones that are there, you can practice them on your own. Is that okay?
Okay, sir.
Okay,
Great.
sir.
Great. So this, we are using another test now. That is the Shapiro-Wilk test, and so the Shapiro-Wilk test uses three parameters: the W, the V, the Z, and then this is the p-value. So again, it is this p-value that you will compare with the alpha value. So alpha value that you choose may be 0.05, and if you compare this p-value with that alpha value, you will see that the p-value is much, much smaller compared to the alpha value. And therefore, you will reject the null hypothesis. So,
excuse me, Prof. Excuse me, Prof. Yes, please. What is the alpha, the range of the alpha value, sir?
Okay, everybody, if you have your paper with you, just write something down. Write alpha. Alpha equals to 0.01 and put comma, 0.05 and put comma, or 0.10. So those are two. Every researcher is the one, and the researcher is the one that chooses his own alpha value. But the common ones that the researchers choose are the three that I've just mentioned: 0.01, 0.05, and 0.10. There are many things I can say, but I am just trying to choose my word so that I don't complicate things for you. So for purpose of taking decision, once you have chosen your alpha value, let's say the alpha value we are choosing now is 0.05, which is usually the one that most researchers in social sciences will choose. You will now compare that alpha value with the p-value that is reported in your test output. And the p-value here is 0.00430. So put it down. I hope, let me see if I can do something to help you. So I'm going to use whiteboard. Let me use a whiteboard. So I'm going to, just a minute. Okay. Are you able to see my whiteboard?
Yes, Prof.
Excellent. So I'm going to give you now what I will call decision rule. I will call it decision rule. So this is your alpha, and your alpha could be 0.01. It could also be 0.05, and it could also be 0.1. Or you say, so researchers will normally choose any of these three, but the popular one is for the researcher to choose 0.05. So when you are now taking your decision, so as a matter of, so at the level of taking decision, so you reject H naught if your p-value, if your p-value is less than the alpha value. If your p-value, that is the p-value reported in your test output, if it is less than the alpha, you reject. So, but do not reject. Do not reject if your p-value is greater or equals to alpha. So you can always use this as the basis for your decision. So in our case, here, this is the p-value. So this p-value is the p-value is far less than the alpha of 0.05 that we have chosen, and therefore we reject the null hypothesis. And what is the null hypothesis saying? The null hypothesis we are testing for, you are not the one that is stating this hypothesis, don't forget. So it is the standard hypothesis. So the null hypothesis is simply saying normally distributed, that the variable is normal. The alternative is saying not normal. So if you reject the null, then of course you conclude that it is not normal. So here, because our p-value is very small and much smaller than the alpha level, so we are rejecting the null, which says the distribution is normal. And therefore, we will conclude that the variable is not normally distributed. So I don't expect any other question. We could.
Sorry, Prof, sir.
Yes.
Sorry, I have a question.
Okay.
Yeah, the convention, please go ahead. The conventional thing that we used to know about non-hypothesis is that the assumption that H naught normally says it is not. So I was expecting that H naught.
I'm telling you that for this test,
okay,
this test is, there are some things I don't want to start going into, but this test, it is not you and I that is saying it. It is the standard way for normality test. Do you hear me?
I'm hearing you very well, sir.
So you cannot come, I cannot also come and put in H not normal. It is not good, it is not valid. It is the way the test is constructed. This is just the simple way I can explain it. I know what you people are talking about, but when we get to another level now, we will talk about it. But for this normality test, it is not about your choice. It is not about this is how hypothesis is constructed. It is the way the test statistic is developed, and I'm also making it more complicated. So, but don't. So when you are testing for normality, the null hypothesis is normal. Is that okay? The alternative is not normal.
Okay.
Whether you are testing for it in Nigeria, in US, in London, anywhere, that is the standard. That is it.
All right, sir. I want to
So it is what you should know. It is what you should know. It is not about this is how they normally know this thing. Is that okay?
Yes, sir. Yes, sir.
I hope nobody will ask me this question again. But it's good you are asking. I can explain why it is so and so on, but we don't have the luxury of time. And in fact, we have just less than 30 minutes now to do justice to the rest of the things we have. We've not even talked about the t-test. No. So I'm going to. Hello.
Yes, Prof. We're hearing you.
So we are going to.
Yeah, Prof. Go ahead. Yeah.
Okay, great. So the stage we are now is I'm going to look at another test. That's the Shapiro. So we won't, all the other code commands that I put there, please, you are the one that will run them on your own. So again, the Shapiro Francia normality test is this. Let me also use the MPG and then let's test. Or you just simply copy and paste here. So this is the command for Shapiro Francia test. So you will see the test also agree that this MPG is not normally distributed, as the p-value is much more smaller than the alpha value. So the three tests, they agree. Whether you use the skewness kurtosis test, or you use the Shapiro width test, or you use the Shapiro Francia test, the three agree. And this is the kind of thing you should always do to be sure that you use different tests to really establish the truth about the distribution. Sometimes these tests, they disagree. So when they disagree, you might want to look at which test is most powerful. Some tests are more sensitive. You might also need to increase the sample size so that the differences might arise because of the sample size and so on like that. So that is all about normality test. We can now move. I don't want to assume that there will be another question. Now the t-test, let me see if I have any. So we have done this. All these other ones that I didn't run, please try to run them and explain your own. So here is where we are, and let me now take you to where you go to statistics menu, and then you go to the classical test of hypothesis. Like I said, this is where we are, and then this is the dialog box for the t-test. I've told you, when you are dealing with one sample, you can deal with one sample or two samples. When are you dealing with one sample? When you have only one variable. So let's say in this case, the variable we are interested in is the MPG. So in this test, you want to, so when you are using t-test, you need to specify the hypothesized mean. So the common one, if I put the hypothesized mean to be equal to 0, so what I'm simply saying is that the mean is not different from 0. So that is this. When I say the mean is not different from 0, you can also interpret that to mean that the mean is not significant. Because if the mean is not different from 0, it only means that it's the same thing as 0. And so you are testing a null hypothesis. We might spend more than the normal time duration today, if you are ready. If I'm testing hypothesis about the mean, and I say, okay, the mean is equals to 0 versus the alternative, and I say the mean is not equals to 0. So this one is the same as saying not significant. And that is the sense you people carry along to say that anytime the null hypothesis is always negative. Yes, but it's not always. So it is not in all cases. People overstate some facts, but that is not in all cases. So in this particular case, fine, it is. So the mean equals to 0 is simply that the mean is not significant. It's not different from 0. So when we say the population value is not, it's not significant, we are actually saying that it's not different from 0. The same way, so if you now reject this null hypothesis, then you can conclude that, yes, the mean is significant. So let's now go back to here. So if the hypothesized value is 0 now, so I'm now saying that the mean of MPG is 0. So let's test this hypothesis, or I can just copy it. You can choose the level you want here. So the common one, the default one, is the 5%. So in this case, when you choose confidence level of 95%, it means the alpha level is 5%, and that is 0.05 that you call your alpha. If you choose, these are other ones you could choose. If you choose 90%, it means your alpha level is 0.01. That is, alpha is equal to 0.01. And if you choose, it means your alpha level is 0.1, not 0.1. Sorry for that. If you choose 99, that's when your alpha is 0.01. So, but the default one, the common one, is 0.05 for alpha, but it will now be 95% confidence for 1 minus alpha. So the opposite of level of significance is the confidence level. So we can copy this and paste that command. So I can test this one. So for one sample test, this is the average of the 74 observations. And this is the standard error of the mean. And then this is the standard deviation of the observation. This is the 95% confidence. This is the lower limit. This is the upper limit. And this is the test. The way I put it, this is the test, which means I'm testing H naught, whether the mean is 0, which means not significant. So this is the computed T value, and this is the degree of freedom, which is 74 less 1. And these are 3 possible alternatives that you can choose from. So if you are interested in whether the mean is negative, this is 2. So if you want to choose whether the mean is, that is for the alternative, because if you say the mean is equal to 0, there are 3 possibilities. One is that the mean is less than 0, or the mean is greater than 0, or simply the mean is not equal to 0. So these are 3 possibilities. And from here, we could even see clearly, because the p-value is 0, though not entirely 0, but because the precision, the level of precision in this result is 0.000000. So that's why it appears to be 0 here. If we increase the level of precision, we will have the remaining values. But let's even say it's 0. So 0 is less than the p-value that we are choosing. That means the alpha value of 0.05 that we are choosing. Therefore, we are going to reject this hypothesis and say that the mean is significant. We will say that the mean is significant. So if the mean is significant, the question is, from this hypothesis, the mean is not equal to 0, so it's significant. Again, we can also see that the mean is actually positive, is greater than 0. So this is how we interpret. This one does not give us the direction. The second one does not give us the direction. It only says there's it's not different from 0. Sorry, it's not different from 0, but it doesn't say whether it's less or greater. But this one is more, the direction is very clear. It says that it's positive. So this is how we interpret this for a single, for one sample t-test. We can change, of course, if we choose, we can change the level of significance. Let me say I want to use another level. So I'm using level of 90% confidence level. And in that case, it means my alpha level will be 0.1. So again, whether I use that, the result is the same. So this MPG, the population mean is not the same as 0. So we reject the null hypothesis that the population mean is equal to 0. And we can conclude that the population mean is not the same as 0. This one establishes that the population mean is actually greater than 0. Okay. We can now, because of time, any question quickly on that? Be mindful of our time, please. Yes. So the next one is when we have 2 samples. So sometimes also we could have two samples. You see something has changed when it's one sample. Okay, before I leave this one sample, let me even assume that the population mean, that I want to test whether the population mean is equal to 20. And I want to use this. So let me check. So instead of 0, I'm testing whether the population mean is 20. So again, here for this test, that the population mean is equal to 20. I can see here now that if I choose alpha level of 0.05 at the alpha level of 0.05, you can see that this value is greater than 0.05. So we know from here this one will not be proper. So we can see this one, the population mean, when population mean is greater than 20, the p-value is 0.05. Sorry, 0.0288, which is less than 0.05 for alpha. So since it's less, we can reject that this is not equal, is not greater than 20. But here we can accept that it is not equal to 20. So the null hypothesis that we are testing here is that the population mean is equal to 20. So in this case, with this p-value, we reject, we accept that null hypothesis. Whereas in this case, we reject that null hypothesis. You simply need to compare that p-value with your alpha value. So with the mean of equals to 20, if we set our alternative not to be equals to 20, then we are going to accept the null hypothesis. If we set our alternative to be greater than 20, we are going to reject the null hypothesis. And so the conclusion here is that at 0.05 level, the mean is greater than 20. So you can also change the level if you so wish. You can change the level and put 90. If you want to change the level to 90 or to 99, maybe to make the test a little more strong. So even at that, if the null hypothesis is saying the population mean is equal to 20, then for this, we are going to accept that null hypothesis. For this, we are going to accept that null hypothesis. For this, we are going to reject that null hypothesis. So all you just need to do is to compare that your alpha value with the probability value. So,
Prof, I noticed that at different confidence interval, the values still remain the same thing. For the three
at different confidence
level, both the 99 and
they cannot be the same. They cannot be the values 90 at 95%. They are different. They cannot be the same. Is that okay? Is that okay? Wow, I can't hear you again. Okay, let's move on to the third one, which is looking at where you have, the second one, where you have two samples using groups. So in this case, I might want to look at MPG. Since foreign, we have a variable that a grouping variable foreign, which group the data into vehicles, MPG vehicles that are foreign, MPG vehicles that are domestic. So this test might now look at situation in the two groups, whether the group of the MPG in group of foreign has the population mean for MPG group in foreign the same thing as the population mean of MPG in domestic. So if we choose MPG here, then the grouping variable is foreign. So the result we are going to get, we compare the MPG in the foreign, the population mean of MPG in the foreign with the population mean of MPG in the domestic. So if I compare, if I run this, this is how to write this. Can somebody please mute yourself if you are not speaking? Let everybody mute himself or herself, please. So this is the command. This is the variable that you are testing, which is the one that must be measured on a continuous scale. But if you have grouping variable, so it allows you to know, to compare the population mean of the two groups. So the grouping variable here is foreign. So if you test here now, so you can see this is in the domestic, there are 52 values of MPG. In the foreign, there are 22 values of MPG. And of course, the combined number of observations is 74. So this is the mean for domestic, foreign, and these are the standard error, the standard deviation, both for the individual group and the combined group, and so on. That this is the confidence interval, and this is the difference between the mean of the domestic and this. And this is the difference we are saying is not is this. If the difference is 0, it means the mean, the population mean of domestic is the same thing as that of the foreign. So this test is actually saying there is no difference between the average MPG for domestic and average MPG for foreign. This is what this test is actually talking about. So it's saying the difference is 0. So this test is also called the test of difference. The test of difference. So it's testing whether the average in the two groups are the same. If they are the same, the difference will be 0. The alternative will be that they are not the same. This is what this one is saying, but it doesn't say the direction. This one is saying they are not the same, but one is that of the domestic is smaller compared to that of the foreign. This one is saying they are not the same, but the direction is that of the domestic is greater than that of the foreign. So we can notice that they are not the same, because if you compare this with your alpha level, you are going to reject the null hypothesis. So they are not the same, but it's even more clearer now here that they are not the same, but the domestic is smaller than that of the foreign. So this is the T test, this 2-sample T test. Here we assume that the variances are equal, but sometimes we also need to test this assumption of unequal, because if we don't, we just assume with this, but in practice it is better for you to check. So if you put option not equal, then it will give you a more precise test. So if you go to statistics, I hope I have it. So if you go to the window, you can simply check this this particular option on equal variances. You can check it so that if you click, you can copy this now here. So the option in the command window, if you don't want to use the dialog box, you can now be able to register the proper command, and this is the command to indicate unequal variances. So nothing has really changed, even with the option of unequal variances. So let's go back again. Not if we use another option, that's Welsh approximation. That is an option you use also for unequal variances. You can try all of this to be able to properly establish. So you will see that even with the Welsh approximation, this result has not changed. Has not changed. So doing analysis this way makes your result robust, and it avoid you avoid the possibility of somebody telling you later to say, did you do this, did you do that? If you have already done it and you have reported it, you provide a more defensive argument than when you have not done it or you don't even know whether you should do it or not. Because of time, we have even exceeded our time. Let's quickly go now to the t-test with 2 sample using variables. This is in the 2 sample using groups. You assume that the variable can be assessed. The variable can be considered among 2 possible groups. But here, in the 2 sample using variables, we are assuming that we can have 2 variables that are measured on continuous scale. So take, for instance, MPG is measured on continuous scale, and we can also notice that the second variable, let's even say price. No, let's say price. So we are looking at variable. So we might be saying these 2, the average, the mean population of the MPG is not different from the mean population of price. I'm just hypothetically. Ideally, when do we use this type? If, for instance, you have I conduct a test for your group now, and after this training, and then we organize another training, and we have another group, and I conduct tests for them. So I can look at whether the mean performance of this group is the same as the mean performance of the new group. So this is the kind of situation when you use this. So the 2 groups, they are actually considered to be independent of one another. So nothing is basically common to them. But in the peer group, you have relationship. So it could be this same group, I conduct a test before the training, and I conduct post-training test. The 2 tests are conducted on the same set of people. So it is this that we call paired. So there is a relationship. Something is this same set of. So the first observation, the second, they are both from the same set of individuals. So they are called paired. So you use this paired if you are doing pre and post evaluation kind of study. So even if I don't run the test, it's the same. That's the explanation, what makes the 2 different from one another. So for the 2 samples, let's say I use MPG and the price. I can simply copy and paste this. So this is how it is. So I'm testing whether the average population mean of MPG is the same as the population mean of price, and the variables are unpaired. In other words, there is no relationship between them. So this is the outcome of this test. So as I said, the mean MPG, this test is saying there is no difference between the mean of MPG and the mean of price. So, and if there is no difference, it means that difference will be equal to 0. This test, based on this, if you use this null hypothesis, then you are going to reject the null hypothesis. If this is your alternative hypothesis, you are also going to reject the null hypothesis, and you will conclude that there is a difference, and the difference is negative. So this one simply tells you that you cannot reject the null hypothesis. So this is how you conclude based on this output. Now, the last thing I will do, because we are just a little bit above our time, let's run the paired one. So I go to classical and I run this t-test. So I put pair here and then select the same set of variables, MPG. I select also price here. In the slide, I use different, you will see the data set I use. You can also use them. They are uploaded already. So I select price and then, I can copy the command and paste. So this is the test. This time, because there is no option of unpaired, it means the two are paired. So again, the result is not different. So the conclusion is not different. So this is the last thing I will talk about, is how do we use this t-test calculator? Because you might need it one way or the other. Sometimes maybe you are reading an article. In this case, you don't have access to the individual values. What do I mean by that? This is our data set. So I have access to the values of prices. I have access to the value of MPG. But there are occasions you don't have access to that. But maybe what to have information about is that you know the sample size. Maybe I know the sample size to be equal to 20. And apart from that, I also know that the standard deviation, I also know that the standard deviation is 15.8. So let me say, I know maybe in the article, that's the information I have, but I don't have information, the detailed individual values. And I also have information about the mean. Let's say it's 62. And then I can now, based on this, say, okay, is this mean the same as a particular hypothesized value? Let me say I'm reading article about that intelligence quotient, and that article reports that the sample size is so. This time, let's say 20, and the article also reports that the average, intelligence quotient for purpose of discussion is 62, and the standard deviation is this. But you don't even have access to the actual observations. But based on this, you now want to test whether this intelligence quotient is the same as your own class. Let's say you know intelligence quotients of your class to be 75. So you now want to test whether the intelligence quotient reported in that article is the same as the one that you know about. So you could employ this t-test function. So it allows you to do the calculation without necessarily using the individual values that you don't even have access to. So you could do that at any level of significance that confidence level that you choose. So you can now run this, or you simply copy here and paste. So it gives you the sample size, the mean reported, the standard deviation reported, and of course the hypothesized value that you want to test. So you can now test. So you can see this test is saying that the mean is equal to 75. So this test, if this is the alternative, that it is less than 75, then you are going to reject the null hypothesis. And of course, if this is the alternative, it simply say it's not equal to 75, and still you are going to reject the null hypothesis. And of course, you can reject the null hypothesis in this case. And therefore, this test gives an indication that it is true that the mean is not equal to 75, but it's lower than 75. That is the conclusion based on this. The other one that you might also, if you have information about two sample too, you can put the two sample here. So in this case, you can choose if in the article it talks about two groups, maybe two groups of animals that are fed with different food types, and then you are able to know the sample, how many animals there are, maybe 20. So then you know the average of the first group is reported, maybe the average is reported as 20, and the standard deviation is reported as 5. And another second group is reported, so maybe the second group is 12 here, and this is 15 as the mean, and then the standard deviation is 4. So you could use this calculator to check, and that is once you click copy here, you can paste. So this is the sample size of the first sample. This is the mean. This is the standard deviation. The second, this is the sample size 12. This is the you can see we separate them by space. So if you don't want to use the dialog box, you could just type them this way. So the STATA will automatically recognize this as two groups. Sample for group 1, this is the size, this is the mean, this is the standard deviation. For group 2, this is the mean, this is the sample size, this is the mean, this is the standard deviation. And so you have this test. From here, we can see that we cannot reject the fact that the difference is less than so we cannot reject the null hypothesis if this is our alternative. But we can reject the null hypothesis and say that it's not equal to 0. And good enough is evidence, it's obvious that certainly the mean of the first one is greater than the mean of the second one, and that the difference is actually positive. So this is the conclusion for this evening. Sorry for the little extra time that we have used.
Hello, Prof.
Thank you, Prof.
Thank you.
I just have one quick question.
Prof. Well done.
Hello?
Yes, please go on. Please go on.
From your notes, there's something that you used as Welch. What does that mean?
Okay, is an approximation method. You know, the moment the variances are unequal, if the variances are unequal, that violates the underlying assumption.
Assumption, okay.
Is that okay?
Yes.
So it means that test can no longer, the word that we use is that test is no longer
appropriate,
optimal.
Okay.
So it has to be, so the approximated procedure, the procedure for approximating it to something that is fairly close is the wedge. So it's an option to improve the precision of that decision. Is that okay?
Okay, thank you, Prof.
You know, because of the violation of the underlying assumption.
Okay.
Yes. So, but if the variances are equal, you don't need that approximation.
Thank
Hello,
you very
Prof.
much.
Yes.
Thank you for the teaching. Please, my own question is on the normality test.
Okay.
Please, if you discover that your data set is not normally distributed,
yes,
is there anything you can do to correct that?
There are many things you can do to correct that. You can transform, the data, but I don't want to go into all those details. But the one simple one I can give you is to use log transformation. So you can take the log and see whether it will be normal. Are you still with me?
Yes, Prof. Thank you.
So if it's normal, then it means when you are doing the test, you are going to do the test on the transformed variable, not the original variable.
Okay, sir.
So you will be reporting on the transformed variable.
Thank you, sir.
Excellent.